AP Stats, what's up? It is Coach Jay, and yeah, I know I'm not here today, and I apologize for that. But I hope that this schedule here and the notes here today help you to stay up on everything and kind of go from there. Yeah, so Coach Jay is with you. We are in the Heat House. Yeah, so as we went through this the other day, I wanted to make sure that we hit on the necessary components that were here. If you remembered this idea of, the idea of the chi-squared test, and I'm actually going to take a screenshot of this just to hold on to. We went through this idea of the chi-squared on the observed and the expected, and we went through all of these components of what is a chi-squared, where we have multiple categories. We remembered that the degrees of freedom of this was n minus 1. And when we remembered that it was n minus 1, we actually went through this idea of knowing that in this case the categories was the n, right? So we knew the categories was n. So when we went to n minus 1, we know that there were 6 categories. Minus 1 would give us a total degrees of freedom of 5. Now, as far as the observed values go, what we found was that 21 were brown. Yellow was 19, 51 was orange, 26 were green, 65 were blue, and then 29, in fact, were red. Okay. Now, when we went to the actual expected, this was where I wanted to make sure that I hit on this part. I'm going to have to take out my calculator, and hopefully this will be quicker for you. But we took each of the probabilities that were there. We took the 0.13 and we multiplied by 211 to get 27 here. Then yellow, we went and on the yellow side we did 19 times 211 to get, I'm sorry, hold up, not 19, I'm sorry, 0.14 times 211 to get 30. We get 0.2 times 211 to get 42. Green was 0.16 times 211 to get 34. 0.24 times 211 got me 51. And on red side, 0.13 times 211 got me 27. Now, when we go to this chi-squared idea, I think it's important to kind of know how to use the calculator here. So we're going to pull this up, and as we go through this, I want to show you real quick on the stat and in our test how to do this, and then we'll kind of work backwards how to do the 4-step process and all of that, and we'll run through that together, okay? So let's go down, down, down. We're on the chi-squared goodness of fit test, okay? So the observed and the expected would be in our L1 and L2. Now, we haven't put that in yet. We know our degrees of freedom would be 5. So let's go ahead into our stat and into our edit, where the expected would be the L2. So we're going to put in the expected of 27, 30, 42. Okay, so I'm going to do this on mine. So 27, 30, 42, 34, sorry, 34, 34, there you go, boom, 51 and 27, okay? My, now I'm going to go back up, go over to L1, I'm going to make sure I clear this, I clear and then go down. This would be 21, 19, 51, 26, 65, and 29, okay? Now on this, you're going to have to show work, but I just want to make sure that you know when you went through it, because you could also find the chi-squared the long way like we did the other day. But we could go ahead down to the chi-squared goodness of fit. We'll talk about why it's goodness of fit here in a second. But we're going to go ahead and draw this. And as we draw this, we're going to see that this is our chi-squared graph, which we talked about the other day. And as we looked at it, we get a p-value of 0.0218 with a chi-squared of 13.17. So let's do this. Let's go 13.17 was our chi-squared value that we should have calculated from the other day, okay? Now, was this idea of randomness, was this thing random? That's the question. Well, yeah, it was, because they were randomly sampled, right? So we would say yes, randomly sampled. Okay? The large counts, which expected count is the lowest? Are all expected counts greater than 5? Well, the large counts is a little bit different, okay? In this instance, the largest expected would be, in this case, largest expected was blue, right? So that was blue in this instance, okay? And because it was blue, we know that in this, all of these values, all expected, have to be greater than or equal to 5. This is our new law of large counts, so to speak. So all expected have to be greater than or equal to 5. And in fact, they are, right? So we would just say that, all expected counts are greater than or equal to 5, okay? So we're good there, all right? That's largest counts. Now, as we go into this next part, we go into this for this test, the degrees of freedom, where n represents the number of categories. We've already said that this would be 5 because it's the categories of 6 minus 1. What is the test statistic for this test? We already said 13.19. And then we can use table C to find the p-value. Now we know, I think it's 0.0219. But table C, when we go over here, kind of look down here, the tail probability, kind of look for it, degrees of freedom of 5. The test statistic, we're going to look for something close, 13.19, which would be about right in here. So they're looking for an area of 0.02. Notice it's always to the right. Always, always, always to the right. So anytime, again, 0.02 would be that area to the right with a test statistic of 13.39 and 5 as my degrees of freedom. So this is 0.02. So again, here's my graph. I go up. Here's my chi-squared graph. Here's my chi-squared test statistic. Here's the area. There's my p-value, the area that's inside. Remember, we start at 0 for this, right? Because no negative values because we square it, right? And when we look at this, we're looking at what the p-value is, okay? All right, so once we get to this, it's pretty good here. We just go ahead and go from there. Also from table C, just remember we go to degrees of freedom and find the closest test statistic and relate it to the p-value, okay? And that's how we found it, 0.02. We got 0.029, 219 on the calculator, but that would work, okay? So making a conclusion as we go to, by the way, this is called, just a heads up, I keep thinking of things. This is called the tail probability. Just make sure you get that down, okay? Now make a conclusion based on the p-value. We could just say, since our p-value, 0.05, okay? Making sure, what was our alpha level? It doesn't really say, does it? Since our p-value is, and I'm just going to do, could be anything. It could be greater or less than my alpha level of blank, right? Because we don't know what it is. It could be 0.05. Since our p-value should be 0.02, by the way, I'm sorry, 0.02, is greater than less than my alpha level of whatever it is. We do or do not have convincing evidence. If it was 0.05, we would have convincing evidence to reject the null and reject the null, and then put a little context in here, okay? Concerning M&Ms, stating that the distribution of colors of M&Ms is what they said, okay? All right. The p-value, remember the p-value is assuming the null is true. It is the probability the test statistic of chi-squared happened purely by chance. Okay? Happened purely by chance. Again, that's the interpretation of a p-value. Not much different, right? Not much different. A lot of times you don't have to put this in the conclusion, but it's good to at least know for that p-value side. It is also the same thing as well. All right. If statistically significant. I'm sorry. Hold up. I could back up. Actually, I'm gonna backtrack. No, yeah. If it was, I'm gonna say, if statistically significant, then state this. All right, here's what you would state. All right, here we go. You would state that the color or category, this would be the category, okay? The color of M&M that was lowest / highest from expected was blank. So what one was the lowest or highest? Well, we could go back here. Okay, so observed to expected. So the expected to observed, which one was the farthest? This was 11 away, 6 away. This was 9 away. This was 8 away. This was 14 away. Yeah, I think the 14 was the highest. So we would say blue was higher, right? The color of M&Ms that was highest from the expected was blue. And therefore, blue contributed most to this being statistically significant. Does that make sense? Because it was furthest away from my expected. I hope that makes sense on that. Hey, let's try this. Do this. Pause the video and try to see if you can do this, all right? Pause the video. Test if you can do this. Go. All right, you're back with me. Here we go. Let's see if you got this. The significance level 0.05, hypothesis, the null and the alternative. Note that there are a couple things that we're not putting up here. Notice there's no statistic. There is no statistic yet, okay? Yet. That's in the do phase. The null is that the color distribution of M&M claim is true. Color distribution of M&Ms is true, right? And we would do the same thing. Don't do this on the test, but is not true, okay? Make sure you put a little context in there as well. The name of this procedure is a chi-squared goodness of fit test. It's important. We'll talk about goodness of fit later on, but really we're just trying to get the fundamentals here. The next thing, is this thing random? Yes. Yes. It is a random sample. Expected are large counts. Expected values are all greater than or equal to 5. Okay? Making sure we're saying that. Man, we could maybe put the lowest. So the lowest, a lot of times we'll put the low one. So the lowest expected was brown. So we just say that brown, which had 27, was the lowest and was greater than or equal to 5. Good? Alrighty. The do phase. Let's go here. Do phase. Picture. There's the picture here. Boom. Good. Here we go. Here's the chi-squared right here. This is our p-value. This is 0. Okay. Love it. Also, they like to put this like the t, the chi-squared 5, which is the degrees of freedom. Remember, degrees of freedom is categories minus 1, which is 6 minus 1, which is 5. That's how we contribute to that over there. Okay. Also, we need the specific formula. Notice there is no general formula. No gen formula here. We go straight into our sum of observed minus expected squared divided by expected. Now, I am able to use a calculator on this. Okay, so I can use a calc, but must show some work. Okay, so make sure you know that. It must show some work. My test statistic was 13.19, and my p-value was 0.021, I think something like that. Okay? All right, so what work would I show? Well, I would show that The observed minus expected squared over expected. Good. Okay. So maybe I take the first one. I've seen this done a couple ways. The observed minus expected would be 21 minus 27. So I might say, okay, 21 minus 27 squared over 27 plus dot, 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 dot. And then maybe you just put the last one there. So the last one would be 29 minus 27 squared over 27. Okay? And that would give you what your chi-squared value would be, which in this case would be our test statistic of 13.19. Okay? So that would be the work. It'd be sufficient. Maybe you would label this as like, okay, this is the brown one and this is the red one, so someone could actually follow that, okay? Accordingly. And maybe also putting the observed and the expected, you might have to put that in the top part as well on there, okay? And then on your conclusion, we can go back to our conclusion. Based on us, we would just say, because our p-value, which in this case was 0.0211, we're going to say our alpha level was 0.05, okay? So we're going to say is less than our alpha level, which is 0.05. We do have convincing evidence to reject the null. And state that the distribution, we accept the alternative, right? Of M&M claim, M&M's claim is not true. Okay? Now, since it's statistically significant, we got to say this now. We would say the blue was the biggest contributor, right? So we'd say the color that contributed, that was the highest from the expected, was blue. Okay? Contributed most into our chi-squared, contributed most to the statistical significance, okay? What's missing, we kind of already said this, no parameter, no statistic, no general formula. Yeah, no general formula. Good job, good stuff. And that would be it right there, okay? All right, here's your golden nugget. Make sure you got kind of each of the parts here of, how to find each of them, 4-step processes. Yeah, I mean, a lot of this is just kind of reviewing and going over it. So you can pause that. Also, I'd like for you to practice this really quick as you go through it. Note that the sample is here, right? That's the sample. The table shows the distribution. Probably that the distribution of car color in Oro Valley differs from. So this would be the, so like right here, this is our sample. So this is like the observed. This is the expected. Okay. So you got to turn this expected into whole numbers. Okay. Cool. You could use your calculator, but just be careful there. All right, do that. Pause the video. Check it out. And I'm about ready to switch it. You're going to see the answer in 5, 4, 3, 2, and whoop! There you are. There's the answer. Check it out. Test it. Yeah, small p-value, because look at that chi-squared. Chi-squared value. Yeah, that would be it. Make sure that back here you make a chart that says something about what is the expected whole numbers. You're going to have to make that chart before I go down yonder. Okay? Here it is again. Hey, here's the deal. Have a great day. Here's what I'd like for you to do. If I didn't say it yet, they're going to be on my table over here. You're going to see that there are quizzes. Make sure you take a quiz. Each person must utilize this or take the quiz. When you're done, staple it, put it back on the left side, and within your group, please make sure it's like groups of 3 or 4. If everybody's in on it, you're not really getting much out of that either, okay? If you end up doing poorly on this quiz, I'll put a grade in. If you do poorly on this quiz, then I'll allow you to come in and retake it sometime next week. The big thing I want to do is just make sure that you get some reps on taking this. So this is one example of repping it out, and then the quiz with the multiple choice is another method as well. Make sure you have no max out for this quiz. Only can use people and your calculators. I don't want you looking up answers or anything like that, okay? All right, well, have a great day, and we will see y'all later. Bye.